What's up? So yeah, I work on a cryptocurrency protocol called Coda now. So if you want to talk to me about that, come up to me. Or we can talk about animations, or we can talk about functional programming. I like all that stuff. So algebraic animations. Are you ready? Before we get into algebra, let's just talk about animations. So they're important, right? They're important because if we do them right, we make our apps fun to use, and if our apps are fun to use, then people will use them, and your product will be successful, yada, yada, yada. But specifically, you can't just throw animations everywhere without thinking. You have to be principled. You have to be consistent. It's extremely important. So, decent-sized organizations, a lot of them have this sort of design language built out where, this is the way we fade out. It lasts for this long. It has this easing curve. This is the way we translate. This is the way we rotate, et cetera. I think enforcing that is a little bit hard right now. And if we thought a little bit more about our animations, maybe we could do better. So anyway, keep that in mind. I want to use this simple animation as our playground. All right. So it's complicated enough to illustrate some problems with maybe existing animation APIs on iOS, but simple enough that we have time to talk about it. So if we look what's going on, first, well, let's wait for it to finish. All right. First, we fade in two views. We shrink a circle. We rotate a square. And then we grow the circle and we rotate back. OK? It's very simple. I think there's a natural way to describe this. So on the left, we shrink a circle from radius 100 to 10 with an ease in out curve. On the right, we're going to rotate a square from 0 to 2 pi degrees with a high ease out curve, maybe with custom control points from our designer. Then we're doing the left and the right at the same time and looping once. OK? And I'm going to denote at the same time with addition. OK? And then finally, we're fading in everything before doing all the animations. So this sequencing, I'm going to denote with multiplication. All right? But if I didn't use those operators, this is sort of like a natural way to explain an animation, right? Like maybe you could get this from your designer. Why is this a good way to describe things? Well, we can think about the pieces separately. We think about the left on the left. We think about the right. We can have two different engineers build those. We can have a third engineer combine the pieces later. There's nothing about the left and the right that leaks into the notion of running them at the same time. I don't care if the animation is on different views, like if the left is on one view, the right is on another view. I don't care if it's two properties on the same view. It shouldn't matter, right? I just want to combine them. And being able to not care about the sort of underlying pieces of our animation just makes it easy to build complex things. It makes it easy to refactor. It scales. We can have multiple engineers look at it. We can have you over multiple months look at it. And I have a talk where I go more into this, but you can click on that later. So this description, I say, is natural and scalable. I don't know. Hopefully you believe me. So remember, this is describing this animation. It's pretty straightforward. We're fading in, shrinking a circle, rotating a square, and going back. All right. It should be easy to build. It should be. Let's try and build it on iOS. Let's use View Animate first. So I want to shrink a circle from 100 to 10 with an ease in out curve. Okay? We do UIView.animate in Xcode. We get some autocomplete. We pick an overload. This one looks nice. We can specify an ease in out curve. You pass what you want to do to this animation block. I'm hiding it behind a function because it's not important. And we have a completion. So this is like how you do animations with UIView Animate. And when the instruction pointer hits this line of code, the animation happens. And maybe that's what you want. But that's not what I want. What we want to sort of build out the animation as described is a way to refer to this thing and use it multiple times. So we can wrap it in a function to do that. So we can wrap it in a function called left, let's say. And this is the left animation. Maybe we also want to pass a completion handler through so that we can chain something on the end of this. So that's the left. The right, we want to rotate a square from 0 to 2 pi degrees with a high ease out curve, maybe with custom control points, okay? So we have this boilerplate we already figured out. We do UI View Animate. Hey, we autocomplete. There's an ease out curve. And we say what we want to do in the animation block. We pass the completion handler through. But this is not what we want, okay? This is not what we want because we want custom control points. We don't want Apple's ease out curve. We want our designer's ease out curve. How do we do that? We use the CA media timing function. We pass it a bunch of control points. It's cut off because that's the point, right? This is a long function name. Then we set some global mutable state, because who doesn't love global mutable state? We begin a CA transaction. We set our timing function. We do what we want to do, and we commit. And this will do what we want. I'm not a fan of side effects, but whatever. Cool. Let's think about parallel composition. So I just want to reiterate, I shouldn't have to care if we're running in parallel, doing 2 animations on the same view or on different views. In this case, we're growing a circle and fading out at the same time. And this is what it looks like, right? UI View Animate tries to make this easy. You can just set the properties you want to set, and if you want to do multiple things, you set multiple properties. This is what they tell you, right? But okay, let's try it. Well, we want to do it with this left and right we defined before, and we want to loop it. Okay, we can call our functions that we wrote, but that's not right. These functions call UI View Animate inside of themselves. So we could rip that out. But then we have to use the same easing curve for the 2 animations, and that's not what we want either. So what we can do is we can make a function again, and then just call the animations on the 2 views, and then and then we pass a completion handler through, and we need to make sure to feed it to the one that finishes last, and so we sort of break this black box. In this case, the animations are the same, run at the same time, so it's fine. And then, okay, now we want to loop it. We want to run it backwards. How do we do that? I don't know. I don't think you can. Not as described like this. So, all right. Let's look at sequential composition. So here, it's acting on the same view again. This example, we're growing a circle and fading it out. Okay? We're doing 2 animations, but we're thinking about it as one. This is what I mean. So in what we actually want to do for this animation that we're trying to build, we want to fade in all the views and then do all that other stuff that we already talked about. Well, we can just use a callback. So if we have this fade in all that we build in a similar way, we can pass things through and just tab a bunch of times if we want to chain lots of things. And there's even a way around this. There's this animate keyframes thing, and you can feed it a bunch of keyframes, and then you don't have to tab when you want to run a bunch of things in sequence. But this is horrible, and I'll tell you why I think it's horrible. It's not obviously horrible, but if you think about it for a second, it's a nightmare. Okay, so we have relative start time and relative duration on all of the keyframes, right? What does this mean? This means I have to know the entire timeline of my animation, okay? So get rid of the black box. I need to know how long each bit is. And let's say I want to refactor and move something at the end to the front. Well, I have to change all the numbers again. So that's kind of bad. And then, all right, even besides that, let's say I define some animation sequencing a bunch of things with keyframes, and I want to do that as a keyframe before something else. Turns out you can't do that. So we say it doesn't compose at all. So this is horrible. Right, this simple animation just totally kind of fell apart. We couldn't do the looping, and we had lots of nastiness. Because of side effects. Side effects are the devil. They're bad. And we had this callback-based sequencing, and we couldn't use the animate keyframes to get around it. And I think the reason that this is hard to use, at least in the way that I'd like to use it, is because animations aren't values. In this case, well, we had to wrap it in a function to sort of make it a value, but we can't manipulate animations. UI View Animate just runs when the instruction pointer hits it. So there's this other thing. There's core animation. This is the advanced thing from Apple. There's this implied trade-off between power and easiness. So this is the powerful thing. let's do it again. Let's try the thing on the left. We want to shrink a circle from 100 to 10 with an ease in out curve. All right, we make a CA basic animation. We set the timing function. There's a constant for what we need. That's great. We can set from to a duration. Okay, and then we also have this extra stuff. Yeah, that's yellow, and it's hard to see. That's the point. That was not the point. It's an accident, but it doesn't matter, right? The point is, there's this extra stuff we have to stick on the end. And you can say, okay, well, you don't have to. Well, I say 99% of the time you want to. What that does, that fill mode forwards and that bool that you have to set also when you set fill mode forwards, it makes it so when the animation finishes, we sort of update our model to that value, which is honestly, like, when do you not want that, personally? Okay. But what's cool about this, we have a value now. We have a CA animation. It's a thing. It's a thing we can poke and manipulate, and that will give us more power. And it doesn't run until we add it to a layer. So great. That's good. We can do the thing on the right. It works fine, whatever. Let's not talk about it. All right. We have values. It would be cool if we could define a function that takes two CA animations and returns a new CA animation that runs both animations at the same time. Yeah? This would be very useful. Well, you can't. Oh, okay. Oh, well. Let's just try and do it for the specific thing that we're trying to do. So we want to run left and right at the same time and loop it once, okay? But now we can define left and right as CA animations. Well, we can make a function again. We can, because they're these values, we poke at them and we say, hey, you should auto-reverse. And then we get that looping. And again, we add it to the layers that we care about. So we add the left to the circle and the right to the square. But this isn't so great. Why is this not great? We destructively modify the animations that we defined earlier. This is not good for code reuse. If someone else is using left and right, what happens? And we didn't really black box here. We sort of, it's the same sort of thing. We're digging in and mutating these underlying animations. I don't like it. Sequential composition. All right. Specifically, what we're trying to do here is fade in all the views and then run some animations. So there is this thing, CA animation group. It seems like the solution to this problem. We can feed it an array of CA animations. We have to open our black box a little bit because we have to set a duration. But you would expect this to work, maybe. And it maybe kind of does, but well, it doesn't. It doesn't for a couple of reasons. One, we couldn't create a CA animation for that animations variable. We had to make it a function. So, what are we even doing? But let's say we could. This won't work because the underlying CA animations act on different views. And so that's a no-no when you use CA animation group. Cool. How do we actually do sequential composition? Well, we, again, destructively modify the left and the right. We set the begin time. We set it to now, the CA current media time, plus the duration of the fade. Then we take the circle and the square, and we add the fade to those layers of the underlying views. And then we call our function, and our function uses left and right, and we've already mutated it to change its begin time. Now we're going to mutate it and set auto reverses on it, and then execute it. And it's just a pile of mush. It's all side effects and globals and whatever, but at least we got it. All right. So yeah, side effects, hidden state, bad. This is a recipe for not reusable code, a recipe for things that don't scale. It's a recipe for making composition hard and ad hoc and making it so it's hard to reuse code. And that's bad. So this thing was supposed to be easy. Look at it. It's like two things moving, This is simple. So let's do it again, but this time let's use a new library, okay? And then I'll dive in and explain it. So shrinking a circle from 100 to 10 with an ease and out curve. All right. Well, what if we linearly interpolate from 100 to 10 in 2 seconds, and then let's stretch time in the beginning, squeeze it in the middle, stretch it at the end. Hey, look, it's ease and out now. And then as values are pumping out, just feed them into something that resizes a circle. Okay. Let's look at the right. I want to rotate a square from 0 to 2 pi degrees with a high ease out curve with specific parameters. Well, I can linearly interpolate between 0 and 2 pi, and then stretch time a little bit and squeeze it a little bit, and I get my ease out curve. And then the values that are coming out, I pump it into this rotate square function. Okay, how do we fade in all the views? We didn't even talk about this in the other places, but it's pretty simple. We linearly interpolate between 0 and 1. We can adjust time. We can squeeze it and stretch it, and we get our easing curve that we care about. And then we can bind the values to the container parent, its alpha property, and that will make it change opacity over time. So how do we compose? How do we say, I have a left animation and a right animation. I want to run them at the same time and loop it once. Well, we can say left plus right dot looped. That's nice. What about I want to fade in and then do a bunch of stuff? Well, I fade in and then do the stuff. It's the same. So all the code for that animation fits on a slide, and that's good. So the code mirrors the natural description, the one that is scalable. This is cool. Animations are values, right? Like in core animation, but unlike in core animation, they're immutable values, and we never have to poke them in such a way that mutates them. And because of this, they compose cleanly, and so that leads to a nice scalable abstraction. And there's this really rich algebraic structure underneath this, and that I think sort of helps its helps the power. It's kind of hard to explain, but I'm going to go on a little aside here and just talk about library design in general. I mean, we can still think about animations, but I think because this scalability, I keep saying scalability, is so nice. It makes your code easy to refactor. It makes it easier to do brain dumps. It makes it easier for you to change. Well, that's refactoring, but it's good. So it lets us define animations on one slide. I think it's important to think about composition first when you're thinking about a library, when you're designing an API. So let's not think about what the animation is, but we want to think about how the animation behaves. So specifically, I guess, with animations, you can either combine them and say, if I have two animations, I can run them at the same time. That's the plus. Or I can do one and then the other, and that's the multiply. But then we can think about how these operations behave, and this is the algebra. So there's this thing I call algebra-driven design. I'm sure someone else has called something like this that before. But again, there's a video where I go into this in more detail. I want to really quickly blast through these algebraic laws. These are the thinking framework behind thinking about how these operations behave. So there's going to be a lot of jargon. Maybe I heard in Russia you learn abstract algebra in school, like everyone does. So that's awesome. I wish I learned it in school. I just had to read Wikipedia a lot. But whatever, you just memorize all these words. So whatever, I'll tell you. Okay, so the first thing. Well, we have this binary operation, the sequence, okay? It's binary, it acts on two animations. Well, what happens if we want to combine three animations in sequence? Well, we can only combine two at a time. So we have to decide how to parenthesize. So in all of these diagrams that I'm going to show, I have this equation at the bottom to sort of illustrate what I'm talking about. So in this case, we're growing a circle, we're turning it red, and then we're fading out, okay? We're doing three primitive atomic animations, and we're combining them together into one. So so we have these three things. We need to run this operation twice. We have to decide how to parenthesize, basically. Like, do we parenthesize the first two or the second two? And in the case of sequence, it doesn't change the meaning if we parenthesize the first two or the second two. Why is that? Well, I mean, you just kind of think about it. Like, I have 3 things, and like I'm doing them one after another after another. I can do like the first 2 and then the next one, or like the first one and then the next 2. So yeah, and if your operation has this property where it means the same thing, when it's parenthesized the first 2 or the second 2, then we say it's associative. Okay, and moreover, if it's a binary operation, then we say the sequence operation forms a semigroup. All right. Jargon, awesome. So now let's think about the next thing, an identity, all right? So what is the animation where if we combine it in the beginning with anything or at the end with anything, it's as if we hadn't done anything at all, right? So we think a bit. In this case, we're growing a circle, and we want something that we can put at the beginning and the end and doesn't change what growing the circle means. Well, what if we coupled duration with the animation specification? Okay, so then we could say an animation with duration 0, doesn't matter what we're doing. If it has duration 0, we can stick it at the beginning or the end in sequence, and it doesn't change what the resulting animation looks like. So that's our identity. And because we also have the fact that the sequence is a semigroup, when we add the identity, we now have a monoid. All right? Cool. Cancellation. Well, we can ask ourselves again, is there something that when I combine it in sequence, I can get back just this like special thing? And I think there is. Let's say we have a canceled animation. It's just a magic value that I'm making up out of thin air. But let's say it existed. And its behavior is such that if I have canceled and I multiply with anything, I get back canceled. Okay? Why do you want this? Maybe is what you're thinking. You can kind of think when you're multiplying integers, sometimes you multiply by 0 on purpose in your code, right? It's the same sort of thing. You can imagine maybe we build up this crazy animation, and then we have a conditional, and in one branch of the conditional, we want to cancel everything and run nothing. So we times canceled, and the other branch we keep it. So there's one use case. Next, all right. Parallel composition. Again, we're adding things 2 at a time. We need to make a decision. How do we parenthesize? Again, it doesn't matter. If we're doing like growing a circle, turning red, and fading out all at the same time, well, they're all at the same time. So we can say like, do these at the same time and the third one at the same time, or the first one at the same time with the second 2 that are all at the same time. So parallel composition forms a semigroup. All right. Again, we can ask, what is an identity? Well, we already have this canceled animation. I think that makes a good parallel identity, don't you? If we have any animation and we run it at the same time as a canceled animation, then we just see the thing that wasn't canceled, right? Yeah, I think that makes sense. So parallel composition forms a monoid. Great. Now we can ask, does it commute? This is something that sequence doesn't have. But if we run fade and grow at the same time, is that the same as growing and fading at the same time? And I say, yeah, the order doesn't matter when you're running things at the same time. So we say parallel composition forms a commutative monoid. Okay. Now we can ask the question, how does sequence interact with parallel? Well, one way to phrase this question is, does it distribute? Is it true that, look at that equation at the bottom, grow times the quantity of red plus fade, like turning red and fading at the same time, is that the same as growing and then turning red at the same time as growing and then fading, right? And we think, maybe it is if I define grow plus grow to do the same thing as grow by itself. So we have that extra condition, but then I think this makes sense. And I didn't pull these laws out of thin air. They're sort of the components of a semi-ring, as told by Wikipedia, but also mathematicians. So a semi-ring has all the qualities that we sort of described earlier. So what is a semi-ring? It's something that demands you define addition, multiplication, 0, and 1, right? In our case, 0 is going to be canceled, and 1 is going to be the trivial animation that has no duration, okay? And then it demands that all these operations behave in the ways that we already talked about. And if that's true, it's a semi-ring, all right? So this is really cool. I'm like freaking out at this point, right? Because it's, well, the story is, I was like, hey, animations should have this algebraic, this algebraic nice shape. What is that shape? It's a semi-ring, all right? So yeah, this sort of gives us the behavior of our library. This is exactly what we want. This is the core of the library. We haven't even thought about what the value should be. But now we can, and now we have some guide rails. So now you use creativity, and you work with smart people. So I met up with Chris Eidhoff and Brandon Williams, and we like iterated on a bunch of designs. They're both into this algebra stuff too. And we came up with something that's really cool, I think. So I will share it. Are you ready? What is an animation? What is it, right? What is it? It's a value that changes over time. That's an animation, a value that changes over time. How cool is that? It's so general and nice. It's a nice little phrase. But we can be a little bit more detailed because we just did a bunch of work to figure out the behavior of animations. We know we want duration in there somehow. So what is an animation? It's either a value that changes over time coupled with a non-zero duration, all right? Or a canceled animation. This is our additive identity. Or a trivial animation. That is one that has no duration. And this is our multiplicative identity and our our multiplicative identity. The additive identity is also our multiplicative annihilator. Okay. So right. So this just captures that duration and adds the canceled. So now we can take this description, and there's a mechanical way to transform it into a Swift data type. Well, into a data type in any programming language that's good. For some definition of good. There's these tools. There's the algebra of data types and parametricity, and I don't want to get into it, but this is what it looks like when we do this mechanical transformation. All right, we're an animation over. What did I say? It's a value changing over time. A value. Okay, so it's generic over A, the value. Cool. It's either canceled, it's trivial, or it's a runnable animation with a non-zero duration. On iOS, we can use CF absolute time for this. And it's a value changing over time. Well, that's a function from time to value. But it turns out if you use time as a number from 0 to 1, a floating point number, then it's really useful. So it's a function from 0 to 1 to A. Okay? Cool. Look at that. Isn't that cool? It's like so short. So what's cool about this? All right, it's immutable. That's awesome. Immutability is good. I mean, yell at me later if you don't think that, but think it. It's true. Okay. So how do we actually get the animation to run? Right. I guess that's important. On iOS, we can use this thing CA display link, and that we can get a callback every time a frame is painted, and we can just call our function and do what we need to do. So that's how you get animations that look like animations that we're all aware of. When you press a button, it does something. Cool. But we can also call this function as, let's say we move our finger across the screen of a phone. So maybe we have like a book, e-book reader, and when we move our finger across our phone, we turn the page of the book. And where the finger is on the phone, like sort of says where the animation is. It's 50% done if your finger is 50% through the phone, right? So that's cool. We can also call this function one frame at a time, feed it into some, let's say, MP4 encoder, and then, or H.264 encoder, and then composite it all together and generate little videos that we can embed in a slide deck to help explain algebraic animations. And that's all those videos you've seen were generated from this library by calling this function and feeding it to an MP4 encoder. So that's kind of a cute Easter egg, I guess. Cool. But so we have the value, we have the data type, but now we need to make it conform to semi-ring. And when we do that, we're basically done. So let's do it. 1 is the trivial animation. We already talked about that. 0 is the canceled animation. We already talked about that. Then we can think about combining two animations in sequence, left-hand side and a right-hand side, and we return a new animation. We switch. If one of them's canceled, it's canceled because it's our annihilator. If one of them's trivial, then we take the other side because that's our identity. Then we could have two runnable functions with two non-zero durations and two value functions. What do? We sum the durations because we're doing this and then that. And then one of them might be shorter. So let's figure out what % of the resulting animation is the first one. That's the ratio. And then we can return a new animation that is runnable, whose duration is the sum. And in our value function, we're going to check the ratio. And if it's less than the ratio, we're going to use the first value function. And if it's bigger, we're going to use the second value function. So this is how we can, as we're 50% way through, we switch to the other animation. And then it essentially runs both. Cool. Great. Parallel composition. There's this extra little thing, like we said, well, maybe we didn't say it yet, but we need to be able to combine our A's, okay? Because this A is a generic thing, you'll see where that comes up, but that's all that commutative semigroup nonsense means. We want to implement parallel composition of two animations. We're returning an animation. We switch. If it's canceled and trivial, trivial and canceled, or trivial and trivial, return trivial. Just do that. It makes sense, I think. If we have two canceled, we return canceled. Yeah, I guess 0 plus 0 is 0. That's kind of why I think that makes sense. Okay, if we have two runnable functions with two non-zero durations and two value functions, now we want the max of the two durations because we're running them at the same time. And then we have to make a decision. What do we do if one of them's shorter, right? I think it makes sense, let's say if one of them's shorter, it just freezes and clamps at the end as the other one goes. So let's implement that. We're returning a new runnable animation with the new duration, and the value function calls the two value functions with a clamp at one, and we have two A's, so we have to combine them somehow, and that's what that constraint said on the other slide. Cool. Then if one of the two is runnable, and when we're combining them in parallel, well, we just take that. Okay. Cool. We're done. Now we validate our laws. What's cool about this algebra-driven design is your tests are insanely fun to write, and they're super awesome and catch every bug. So there's a library called QuickCheck. In QuickCheck, you can say, for all x, y, and z animations, x times y times z, parenthesized one way, equals x times parentheses y times z. You literally can write out the properties. It's cool. And then we have basically the core of the library. There's one extra bit that you need category theory to sort of, I guess, know about or whatever. I mean, we've all seen map before. So this is really useful because if we have an animation that computes floating point numbers over time, that's a value over time. That's an animation, I'd say. Maybe you can print it out to console. But it's not something we want to do often. However, it's useful maybe to map that into something that sets the radius of a circle in a view. And then we actually have an animation that we want to use. So, okay, this is the core of the library, all right? And if you build a library like this, you can have a combinator layer that you include in your library. So, for example, we can have a reverse property. What does this do? It gives you back a new animation that just calls the run function with 1 minus the progress. And then it effectively runs backwards. We can loop. How do we loop? We do self times self dot reversed. We can implement delay. We can implement linearly interpolate from a CG float to another CG float in a certain amount of time and give me back an animation of CG floats that when you combine two that are the same, they average. But then you get something where grow plus grow equals grow. So that's cool. But yeah, this is sort of the library that you distribute, right? Other people download your library, hopefully, whatever. And then what's cool is you can have your design team or that one engineer that works really closely with your designers and doesn't build out product features, build this consistency layer. So we can have the fade out. This is the one and only fade out that our app uses. It has this specific duration. It has this specific easing curve attached to it. This is our translate. This is our rotate. And you check it with your designer, you make sure it's right. And then when you're hacking away on product features or someone else's, maybe someone who doesn't care so much about the design guidelines, they just use these primitives and they're to spec naturally. So that's really cool, I think. So building a library like this, you empower consumers to do cool stuff. At this point, I would have liked to maybe show a complex animation here, but I'm not a designer, so I did something else that I think is cool. So because we have this algebraic structure for our animation, we can take the free version of a semi-ring. We can make a free semi-ring. All you algebra students maybe remember, I don't want to go into it, but it's a way to declare the structure in such a way that we can inspect it later. And then we can build a system, as you see here, where I can say, okay, I have 3 actors. I want to center them in the screen, and then I want to make this timeline view that shows what animation is happening at a certain amount of time, and then as the animation goes, it paints in. Okay, and this was really easy to write, surprisingly. I mean, really, this is like the meat of it. It's this intervals function. So you feed it a free semi-ring description of the animation. It gives you back an array of intervals with a name and a start and end point. And from that, it's very easy to paint the timeline as the animation goes on. It's not easy enough that you don't make a mistake like I did. See those bottom 2, the way that it animates in is buggy, and I fixed that, but I didn't re-render this MP4 video. But the point is, whatever, it's cool. Takeaways. Solving problems by composing small independent pieces is awesome. It's natural. It's scalable. It makes it easy to refactor code. Life is good. Everyone's happy. UI, View Animate, and Core Animation don't let us compose animations, and so we can't implement animations in the way that I would like, with this sort of natural description where we don't have to think about the underlying pieces when we're combining them. But we can do better if we look at algebra, and not just for animations, but really for anything. And I'm like super into this, so like come talk to me and we can talk about other cool applications of this. And these types of libraries empower your API consumers to not just build, let's say, complicated animations in a way that makes your code not complicated, but also, you can like make a free structure and traverse it to build out those diagrams. Cool. Thank you. That's my name. That's my Twitter. Here's a link to the library. There's a link to the slide deck. That's it. Questions?
Wow. Thank you, Brendan. All right, questions there. The mic is coming.
Hi, very nice. I was advised to come here, never regret. I'm previously Coco Studio developer. You probably know it's like a famous game engine. And in game engines, there is a natural concept of time. Like there is a run loop that comes with the time frame, and you update everything to the time point of the time. And we had the concept of actions. There's an action that goes moving to the stuff. And it's just funny how I actually did basically just the same that you did a few years ago. Because I wanted to, I had different motivation. I wanted to eliminate ARC overhead of Swift. So I made all the actions value types. And I had an animation that you can call and it returns combined with another one. You can call then or scale, then you can call reversed, and the whole thing is reversed. And as engine feeds you a timestamp every frame, so you just compose it values. So it's just funny how I don't know if you were acknowledged about the same concepts in a game engine, because it's
I didn't actually.
Yeah, it's just
really
it's just basically the core stuff in all game engines in terms of animation.
Cool.
And actually the sprite kit has kind of the same thing.
Oh, really?
But it was super engaging to see how you went totally different way to see and come to the same solution. So it was super great.
Awesome. Thanks.
Cool. Other questions? Right.
So thanks. This was really interesting. So what I thought about, because you have different animation thread when you use CA animation. So maybe we couldn't get away with your abstraction in many apps.
Because so there is imagine a world in which I wrote a lot more code, but I didn't. But you could imagine that. Let's see if I can go back to this. What if? Okay, maybe I shouldn't go back to this. Okay, what if instead of implementing basically we can change the value type. Like we can change the representation of the value without changing the semi-ring. All right. Imagine if we define 1, 0 multiplication and addition over a type that represents core animation instructions that we feed to that we can feed to the animation thread, or even more interesting, what if we build up this abstract syntax tree that then we can perform optimizations on? For example, because we have the distributive law, because grow times the quantity of red plus fade is the same as grow times red plus grow times fade. You can imagine a user might find grow plus whatever, the second one, the one where grow is twice, more cleaner to write in their code. We can optimize it to fewer instructions by factoring out the grow. We can factor out the sequence from the multiplication, the sequence from the addition, whatever. Anyway,
so
you could, yes.
Have you tried to do that with the CA library?
Yeah. I've talked about it with someone who's really knowledgeable about core animation, and they said it was possible, but we never sat down and did it.
Okay.
But I encourage someone to do it, please.
So do you have the sources of this thing?
Yeah. There's. I'll leave it on the slide with the link to the sources. But really, you want to sort of start over, still implement the same protocol, but come up with a new value, a new data type, and and go from there.
Thanks. That's
Sorry for the crazy answer there.
Right. We've got one more question over there. 2 question. Sort of. Let's try.
Hi, thanks a lot for your talk. The question is about, some kind of which overheads introduced by this approach.
Yeah.
Because as I understood, you feed each some kind of frame into this function, which translates. You understood the question?
Yes, I understand the question. So first of all, disclaimer: I am not a very knowledgeable iOS UI person, but I've talked to people who are very knowledgeable, and apparently using CA display link is a thing that people do. So that's why I think it's okay to do. But I actually don't know what the performance trade-offs is with using something like CA display link to do your animations versus obviously core animations faster. But I don't know the specifics of when you'd want to use one over the other. But I'm sure people who are really good at iOS will know the answer to that. So there's kind of an answer.
Thanks.
All right. Any more questions? All right. You can follow Brendan to the discussion zone and ask more algebra or crypto questions.
Or cryptocurrency, algebra, functional programming.
Yeah, everything.
Everything.
So, Brendan, what's the best question? Whom do we give a book?
The second one.
Making it hard for me, right? No, you. Okay, second question. Who asked a question? Oh, yeah, right there. Awesome. Well, give it up for Brendan again. Thank you.